Okay, so if you have a graph that's showing you a kind of curved relationship, for example, exponential growth of the cell number within a given time, okay? So, which is fine. I mean, you can still use that exponential, I guess, equation in your estimation, in your standard curve. But if you want to use a linear graph instead of a curved exponential graph for your standard curve, then there's a way to convert your curved graph to a linear form. Okay, so that is if you change the natural number on your y-axis values. Okay, change that to maybe log entries. Okay, so if you are dealing with Excel, there's a way to do that automatically by clicking on the y-axis values and converting that from natural number to log. Yeah, okay, if you make that conversion, then yes, this curved line will be automatically adjusted to a linear form. Okay, and then from that linear line, you can generate an equation, which will be, just a linear equation. If you want, you can get that. So there's an option of that. And another option is, it's kind of a manual way, when you plot a graph. Okay, so you can use a log paper, which we don't do anymore because you use softwares. So if you use something like log paper, what's the unique thing about log paper? The y values have kind of very strange spacing. Okay, instead of going 1 to maybe 10, 20, 30, it's going like 1 to 10, and from 10 to 100, 100 to 1000. So that increment is different. If you plot your y value on a log paper, of course, you're going to have a linear line. So that's another possibility. Another curved relationship you can get is, what if you have something like this, a decay of radioactive isotope. So radioactive isotope like P32, S35 comes with a strong radiation energy, right? But the thing is, those radioactive isotope has a certain half-life. Half-life means every given half-life, the radioactivity will reduce to a half. Let's say if P32 has about 14 days of half-life. Okay, let's say you had about 500 microcurie of radioactive activity when you received that P32, but after 14 days, that 500 microcurie per, whatever the amount you have, will decrease to a half of that. Maybe you only have 250 microcurie activity, right? So that's a decay of radioactive isotope in every half-life. So the half-life is that. Okay, so if you have something like that, yes, then you're going to see a kind of curved line. So instead of going like this, you're going to have a decreased curved line showing up. So that's going to be, again, exponential decay that will show up. Again, you can change that to a linear form the same way using a log entry. Okay. Okay, that's the end of the graph. You will get to plot multiple graph throughout this semester because you will be using a lot of standard curves. So starting from lab 3, you will get to use Excel spreadsheet, and you will start plotting about 3 different graphs for that lab alone. And the lab 4, you will be plotting a standard curve from your assay of protein standard and then DNA electrophoresis. You'll get to do a lot of those. Hopefully you'll master that skill. Okay. And then we'll also talk about the light measurement because, light measurement based on spectrophotometry is used a lot in many types of assays. So it's a very handy tool. One of the fundamental assay skills are built around spectrophotometry. So you need to learn how to use them accurately. Okay. So light-based measurement. Okay, light comes in different wavelengths, right? So gamma radiation is a form of light, X-ray is another form of light, UV light, visible light, infrared light, microwaves, radio waves, all different light energy within big spectrum. Okay, they carry different potential energy. Okay, so different types of electromagnetic radiation, electromagnetic spectrum. Okay, which covers all these. Okay, light travels as waves, of course. So I'm talking about this right now, right? So there's a cosmic, light which carries a lot of energy. So if you are exposed to cosmic light, the tendency is you'll develop cancer. When we talk about pilots, flying jet airliners a lot, they have better tendency of developing cancer because they are frequently being exposed to cosmic light because they're going through the North Pole area often. Okay, and because there's a lot of energy carried by cosmic light, and then they can damage the DNA. Gamma radiation, same way. X-ray, UV, there's more energy carried by these types of light. And then UV light, the light you can see through your naked eyes is about this much. And infrared, the light wave with much more longer wavelength, micro, UHF, VHF, it goes along that way. Okay, that's the light spectrum. Okay. So the shorter the path of the wavelengths, it carries more energy. Okay, so they carry different amount of light, the energy, and then among those different light wavelengths, spectrophotometry will use visible light portion and UV light portion. Okay, we're talking about here UV, ultraviolet, or visible light. Okay, those two forms of light are being used in the spectrophotometry. So in forms of 380 nanometer up to 780 is the visible light spectrum range, and the UV light is between 180 and all the way up to 400 nanometer range. Okay, so UV is of course stronger than visible light. Okay, and UV light comes in three different forms: UVA, UVB, and UVC. Which one is the strongest? Probably UVA. The tanning booth light, I guess it's the weakest light, I'm sorry. But UVB is still strong enough. You can cause skin cancer if you're exposed to UVB a lot. UVC is the strongest UV light, normally used for germicidal. So if you have a biosafety hood with the UV light, so that light stick will generate the UVC. It can, get rid of bacterial cells, whatever the contaminants that may be found from the biosafety hood's walking surface. Okay. So interaction of light with matter. So what if there isn't matter, okay, in the pathway of the light? What happens when the light energy strikes that matter? So light can hit that matter, and then when that happens, the light can be transmitted through that matter, or light can be reflected by hitting it and coming out on different angle. Okay, or light can be scattered when it hits, and one light goes in, it can come out at multiple light energy. Okay, or the light energy can be transferred from the light to the matter itself. So there's a transfer of light energy that can happen. So there are all different possibilities when light energy is exposed to matter. So that light absorbed by matter and opposite concepts, the amount of light that's transmitted through of the matter is the basis of spectrophotometry, especially when that matter is dissolved in a solution form. That's how you're going to use the spectrophotometry measurement. Okay. So let's see. Again, spectrophotometer, it's a kind of box with this light bulb, okay, on one side. From the light bulb, the lining will be shine. So there will be some kind of a slit that can choose either visible light or UV light, whatever the light you're going to use for your measurement. And then this prism will select certain light wavelength for your measurement, okay. And then there's a little slit that selected light will go through, and then there's a chamber where you're going to place your sample that's located in a special sample holder called a cuvette. Cuvette is made up with either glass or quartz, so the cuvette itself is not going to absorb or transmit light. It's not going to absorb light, and then inside of a cuvette there will be a liquid form of the sample floating in there, and the light will travel through your sample. So either light will be absorbed by your sample, that's the dissolved liquid, or the light will penetrate through, that's a transmitted. So the other side, the amount of light that's transmitted through will be detected on the detector. Okay, so that's the simple design of the spectrophotometer. Okay, so in this measurement, so the sample is in the liquid form. Okay, like I said, that's held in a cuvette special container. So if the object matter is liquid, the light can either be absorbed or transmitted. That's it. It's not going to be reflected. Okay, so there are only two possibilities. Okay, so spectrophotometer takes liquid samples and measures the amount of light that's transmitted through the liquid sample. That's what it's measuring. Okay, so then what is there a relationship between the amount of light that's transmitted and the amount of light that is also observed? The answer is of course yes. Okay, so the machine itself, the spectrophotometer, measures the amount of light that's transmitted. Okay, so which is the light transmitted through the sample. That's divided by light transmitted through the blank. Blank means what? So in this measurement, okay, so the blank is again held in the same cuvette, okay, special container, and then that cuvette has the liquid, okay, without your sample. Okay, so it's like a control treatment. So the only difference is the blank has everything except for your sample. Okay, the solvent and cuvette, everything is the same. So the sample is the only difference. Okay, so the transmittance between your sample dissolved in the liquid and held in a cuvette, and its transmittance is compared with the same cuvette that has the solvent only without the sample. Okay, that'll be the transmittance of your sample only. Okay, that'll be measured from your spectrophotometer. That'll be expressed as a percent transmittance. Okay, equals transmitted times 100%. That's normally how the spectrophotometer detects the amount of transmittance. But if you ever use the spectrophotometer, actually the readout from your spec is not going to be given to you as a T transmittance value. Instead, it's going to given to you as an observance value. Okay, because there will be a conversion of a transmittance to observance happening automatically inside of a spectrophotometer. Okay, because there's a correlation. Okay, so observance is calculated based on the transmittance because there's a relationship. Observance equals negative log 10 of transmittance. That relationship exists between the observance and transmittance. That mathematical calculation is converted inside of a spec, and when the spectrophotometer is giving you the readout, it's going to be given in a form of observance. Okay, the reason is transmittance doesn't have the linear correlationship between the concentration of your analytes, but observance does. That's why spec prefers giving you the readout in the observance instead of transmittance. Okay, so anyway, so when you get a reading from the spectrophotometer, it's going to be always in the units of observance. Okay, and then you're going to use that observance value to compare maybe the concentration of your sample. Okay, that's going to be the data set you're going to get. Okay, that's what the spectrophotometry analysis you're going to do. Okay, so in your spectrophotometry, of course, you have to have the machine spectrophotometer itself with a good light bulb, either tungsten or deuterium light, because they are needed to generate visible or UV light. You also should have a special sample holder. We call them cuvette. Okay, because cuvette they don't absorb the light by themselves. Okay, and then you should also provide a blank. Blank is what? The same sample, it has everything the same, like a solvent it has the same, but it doesn't have the sample itself. Okay, so everything else is the same, but the sample is not present in the cuvette. Okay, why do you need that? Because the blank will give you the baseline. Okay, if you don't have a sample, it's going to give you the zero observance. Your zero observance will be made with the cuvette that contains the blank. Okay, and then cuvettes are made of with, like I said, either glass, plastic. Yeah, there are some disposable plastic cuvettes as well, or quartz. Okay, and glass and plastic cuvettes are good if we are going to use the visible light range observance. Okay, but they are not good if we are using the sample observance in the UV light range. Okay, so don't use plastic cuvette for the UV light observance. For example, like a DNA RNA analysis, you're going to use a UV light, then you cannot use a plastic cuvette. Plastic cuvette is only good for the visible light. Glass cuvette is good for both visible and UV. Quartz cuvette also is good for both. Okay.